Every aircraft you have ever flown on was designed using an equation that has never been proven to work. Every weather forecast you have ever checked, every simulation of blood flowing through a human heart before a surgeon decides where to cut, all of it runs on a single set of equations that nobody on Earth can prove will not catastrophically fail. And I need you to understand what I mean by fail, because I do not mean gives a slightly wrong answer. I do not mean off by a few percent. I mean the math itself breaks. The numbers go to infinity. The equation that is supposed to describe how water moves instead produces a result that says a tiny region of fluid is spinning infinitely fast with infinite energy in a finite amount of time. A mathematical singularity emerging from perfectly smooth, perfectly reasonable starting conditions. That is what mathematicians mean when they say an equation blows up. And after 200 years of using these equations to build everything from jet engines to hurricane models, we cannot prove it does not happen. The Navier-Stokes equations, if you have heard of them at all, you probably heard they are one of the Millennium Prize Problems, 7 of the hardest unsolved problems in mathematics, each carrying a $1 million bounty from the Clay Mathematics Institute. What you probably did not hear is that of those 7 problems, only one has ever been solved in 26 years. A reclusive Russian mathematician named Grigory Perelman proved the Poincare conjecture in 2003, was awarded the Fields Medal and the $1 million prize, and turned both down. He said he considered another mathematician's contribution no less than his own, and then he withdrew from mathematics entirely, disappeared. Last anyone checked, he was living with his mother in St. Petersburg. That is the kind of person it takes to solve one of these 7 problems. And nobody of that caliber, nobody of any caliber, has managed to solve Navier-Stokes. What nobody told you is that the reason it remains unsolved is not because mathematicians have not been trying hard enough. It is because every serious attempt to prove these equations are well behaved has either failed, been publicly retracted in humiliation, or worse, revealed that the problem is deeper and stranger than anyone previously understood. I spent an unreasonable amount of time going down this rabbit hole, reading papers I had no business reading, and honestly, the deeper I went, the less comfortable I became with the fact that modern civilization runs on a handshake agreement with an equation. We use it because it works. We cannot prove it should work, and there is a growing body of evidence that suggests something genuinely unsettling about why it might not. Let me put some numbers on this so you understand the scale of what we are talking about. Boeing designed the 787 Dreamliner by cutting wind tunnel tests from 77 down to 11 and replacing the rest with computational fluid dynamics. That means a computer solving the Navier-Stokes equations around a digital model of the aircraft, calculating how air moves over wings and around fuselage at hundreds of miles per hour. The global market for this kind of software is over $2.5 billion a year and climbing toward $5 billion by the end of the decade. The European Centre for Medium-Range Weather Forecasts, the organization that produces the most accurate weather predictions on the planet, runs one of the largest supercomputer systems in Europe. 30 petaflops of processing power, 80 million euros worth of hardware, all of it doing one thing: solving Navier-Stokes equations across a grid of the entire atmosphere 4 times a day to produce the forecast you glance at on your phone before deciding whether to bring an umbrella. During the COVID pandemic, researchers used Navier-Stokes-based simulations to model how respiratory droplets travel through indoor spaces, and those models directly influenced ventilation guidelines that were applied to hospitals, schools, and office buildings worldwide. Surgeons rely on patient-specific blood flow simulations that solve these equations with blood modeled as an incompressible fluid to predict whether a cerebral aneurysm will rupture. Formula One teams are capped at 30 teraflops of CFD computation per testing period, specifically because unlimited access to Navier-Stokes simulations would make physical wind tunnels obsolete. All of this, every flight, every forecast, every medical simulation, every wind turbine placement, every bridge designed to withstand crosswinds, all of it depends on an equation that carries $1 million prize for anyone who can prove it does not break. And the prize has been sitting there, uncollected, since the year 2000. And here is the part that nobody is talking about. There are mathematicians who now suspect that this problem might not merely be unsolved, they suspect it might be, in a precise mathematical sense, unsolvable. Not because humans are not clever enough, but because the equation itself might be capable of behaviors that no finite proof can ever fully characterize. I realize that sounds abstract right now. It will not sound abstract by the end of this. Because when you understand what that actually means, and what it implies about every system you depend on, the ground shifts under your feet a little, and it does not shift back. But this story does not start with $1 million prize or an abstract mathematical crisis. It starts with a Frenchman who got the right answer for the wrong reasons, and whose own bridge collapsed into a river. Paris, 1822. A civil engineer named Claude-Louis Navier stands before the Académie Royale des Sciences to present a paper. He is 37 years old, the son of a lawyer who died when Navier was 8, raised by his uncle Émile Gauthier, who happened to be the most prominent civil engineer in France. Navier entered the École Polytechnique in 1802, ranking 116th out of the incoming class. By the end of his first year, he was in the top 10, tutored personally by Joseph Fourier. He was brilliant, but not in the way that gets remembered. He was a builder, a practical man who believed mathematics could tame the physical world. The paper he presents on March 18, 1822 is titled Mémoire sur les lois du mouvement des fluides, a memoir on the laws of the motion of fluids. He is trying to extend Euler's equations for ideal, frictionless fluids to account for the internal friction that real fluids exhibit, the way water resists being stirred, the way honey pours slow, viscosity. And the way he does it is by modeling the forces between individual molecules of the fluid, the tiny attractions and repulsions at the microscopic level, and working out how those forces affect the bulk motion. And here is where I personally think this becomes the most underrated part of the entire story, the part that never makes it into the popular accounts. Navier's model of how molecules interact was wrong, not slightly off, fundamentally incorrect. He had no concept of shear stress as we understand it. He was not describing internal friction in any modern mechanical sense. His picture of what was happening at the molecular level does not match what we now know fluids actually do at that scale. But the equation he produced is exactly correct. The mathematical form he arrived at, through a derivation that should not have yielded the right answer, is precisely the equation we still use 2 centuries later to model every viscous fluid on Earth. He got the right answer for the wrong reasons, and nobody realized it at the time. 4 years later, Navier designed something that was supposed to prove his philosophy that mathematics could master the physical world, a suspension bridge to cross the Seine near the Hôtel des Invalides, in a single span of 155 meters. It was technologically radical, a monument to the power of mathematical analysis applied to structural engineering. Construction began in 1824. Then, On the night of September 6, 1826, a water main ruptured near the underground anchorages. The foundations flooded. The towers tilted toward the river. The Paris Municipal Council, which had opposed the bridge from the beginning, seized the disaster as justification to cancel the entire project. Navier was publicly blamed. A government committee formally chastised him for, and I am not making this up, relying too much on mathematics. The man who gave humanity the equation that governs every viscous fluid on Earth, the equation that would eventually be used to design every aircraft, predict every storm, and simulate blood flowing through human arteries, had his career destroyed because his bridge fell into a river and the government told him he was too theoretical. He never built anything significant again. He did at least get his name engraved on the Eiffel Tower, which I suppose is something. 23 years after Navier's presentation, across the English Channel, an Irish mathematician named George Gabriel Stokes independently arrived at the exact same equation. Born in Skreen, County Sligo, the youngest of 8 children of an Anglican rector, Stokes graduated as senior wrangler at Cambridge in 1841, meaning he scored higher on the final mathematics examination than every other student in the university. His 1845 paper on the theories of the internal friction of fluids in motion rederived Navier's equation from completely different assumptions. Where Navier modeled individual molecules, Stokes treated the fluid as a continuous substance, infinitely divisible, and used the relative motion of fluid elements and continuity arguments to arrive at the viscous term. He acknowledged that Navier, Poisson, and Saint-Venant had obtained the equations before him through different methods, but argued his derivation rested on sufficiently different foundations to warrant independent publication. 2 men, 2 countries, 2 fundamentally incompatible physical pictures of what a fluid is, and the same equation. Stokes went on to hold Newton's chair at Cambridge for 54 years and served as both secretary and president of the Royal Society. Navier got a disgraced bridge and a posthumous line on a tower, and the equation they produced, the equation that now bears both their names, is in some ways deceptively simple. It is Newton's second law, force equals mass times acceleration, applied to a tiny parcel of fluid. That is all it is, but the devil is in the details of what forces act on that parcel. There are 4 things happening to any tiny parcel of fluid at any moment. First, the parcel is changing its velocity over time at whatever fixed point you are watching. The fluid speeds up or slows down. Second, and this is the source of all the trouble, the fluid carries its own velocity. Think about what that means. A parcel of water moving to the right is also carrying its own rightward motion into whatever region it enters. The fluid is not just being pushed by external forces. It is pushing itself. It is advecting, carrying, transporting its own momentum. This is the nonlinear term, and it is what makes the Navier-Stokes equations fundamentally different from almost every other equation in physics. In most equations, the thing being described does not influence its own description. In Navier-Stokes, the fluid's motion determines where the fluid goes, which determines the new motion, which determines where it goes next. The equation feeds back into itself. It is a snake eating its own tail. Third, there is pressure. Fluid moves from regions of high pressure to regions of low pressure, the same way you feel wind when a weather system moves through. The pressure gradient pushes the fluid parcel. And fourth, there is viscosity, the internal friction of the fluid. Neighboring parcels moving at different speeds exert drag on each other, smoothing out differences in velocity. Viscosity is the calming force in the equation. It takes sharp gradients and softens them. It takes chaos and damps it. If viscosity were the only thing acting on a fluid, nothing would ever go wrong. The solution would smooth itself out and eventually go still. Viscosity is linear, predictable, well understood. The problem is the second term, the nonlinear transport, the fluid pushing itself. That term can concentrate energy, amplify gradients, and create complexity faster than viscosity can smooth it out. The entire Navier-Stokes existence and smoothness problem reduces to a single question. In a fight between the nonlinear term creating chaos and the viscous term calming it down, does the calming force always win? In 2 dimensions, yes. Ladyzhenskaya proved it. In 3 dimensions, nobody knows. And the mechanism by which the nonlinear term might win, the mechanism by which chaos might overpower calm, is vortex stretching, which only exists in 3 dimensions. I have been obsessed with this topic for weeks now, and I think the reason it keeps pulling me back is that it is not just a math problem. It is a problem about whether the universe is fundamentally tame or fundamentally wild, and whether the mathematical language we use to describe it is adequate to the task. Most of physics operates on the assumption that if you write down the right equation and solve it carefully, you get the right answer. Navier-Stokes is the place where that assumption might break. But here is the thing that matters. Neither Navier nor Stokes proved that their equation always gives sensible answers. They assumed it did, because the equation seemed to match what fluids actually do in the real world. The water flowed the way the equation predicted. The air moved the way the math described. Good enough. And for nearly 2 centuries, good enough is exactly what it has been. Every engineer, every meteorologist, every computational fluid dynamicist who has ever used the Navier-Stokes equations has done so on the assumption that smooth, well-behaved initial conditions produce smooth, well-behaved solutions. Nobody proved it. Everybody assumed it. That assumption is now one of the 7 most important unsolved problems in all of mathematics, and the history of people trying to prove it is not encouraging. On May 24, 2000, at the Amphitheatre Marguerite de Navarre in the Collège de France in Paris, the Clay Mathematics Institute formally announced the 7 Millennium Prize Problems. The institute had been founded 2 years earlier by Boston businessman Landon Clay and his wife, Lavinia. A scientific advisory board that included Fields medalists and some of the most accomplished mathematicians alive selected the 7 problems. Princeton mathematician Charles Fefferman, himself a Fields medalist, wrote the official problem statement for Navier-Stokes. Fefferman's statement is precise and offers 4 paths to the prize. You can prove that smooth solutions always exist for all time in 3-dimensional space, starting from any smooth initial conditions. Or you can prove the opposite. You can find specific smooth initial conditions from which the solution inevitably blows up, becoming infinite in finite time. Either direction collects the $1 million, but you have to prove it rigorously. And his conclusion was blunt. Since we do not even know whether these solutions exist, our understanding is at a very primitive level. Standard methods from partial differential equations appear inadequate to settle the problem. Instead, we probably need some deep, new ideas. That was written in the year 2000. 26 years later, those deep, new ideas have not arrived. I want to slow down here because the Millennium Prize statement matters, and most people who have heard of this problem do not actually understand what is being asked. The question is not whether the Navier-Stokes equations are correct. Nobody seriously doubts that. They match experimental observations of fluid behavior with extraordinary accuracy across an enormous range of conditions. The question is something subtler and in some ways more disturbing. The question is whether the equations, when given perfectly smooth and reasonable starting conditions, always produce solutions that remain perfectly smooth and reasonable for all time, or whether there exist starting conditions from which the equation's own internal dynamics drive the solution toward infinity. Think about what blow-up would mean physically. It would mean that somewhere in the solution, the velocity of the fluid becomes infinitely large at a single point. Not large, infinite, in finite time, starting from conditions that look perfectly normal. No external force pushing the fluid to extremes. No boundary condition creating a singularity. Just the fluid, following its own equation, and the equation saying that at this point, at this time, the speed is infinite. In a real fluid, that cannot happen. Molecules have finite mass and finite speed. At some point, the continuum model of the fluid breaks down and you have to think about individual molecules bumping into each other. Physics imposes a natural flaw below which the continuous math stops being a valid description of reality. But the Navier-Stokes equations do not know about molecules. They describe the fluid as a continuous substance, infinitely divisible, all the way down to arbitrarily small scales. And the question is whether that idealized mathematical fluid can do something that no real fluid ever would. Whether the abstraction can break even when the reality it describes cannot. This is why the problem is so philosophically loaded. If smooth solutions always exist, it means the continuum model of fluids is mathematically self-consistent. The idealization works. The abstraction holds together. If blow-up occurs, it means the equations contain a flaw that is not a flaw of the physics, but a flaw of the mathematical framework. The map has a crease where the terrain does not. And the question is whether you can trust a map that has creases, even if you happen to be walking on flat ground. Pfefferman's conclusion in the official problem statement was unusually candid for a formal mathematical document. Coming from a Fields medalist writing for the most prestigious prize in mathematics, the phrase, "very primitive level," is remarkable. He was not being modest, he was being accurate. After 178 years of the equation's existence at that point, the mathematical community's understanding of its most basic properties was, by Pfefferman's own assessment, primitive. What has arrived is a graveyard of failed attempts. In September 2006, Penny Smith, an associate professor at Lehigh University, posted a paper to the arXiv claiming to have proved that smooth solutions exist for all time. The title was bold, Immortal Smooth Solution of the Three-Space-Dimensional Navier-Stokes System. Nature ran a news brief. The mathematics community held its breath. 12 days later, Smith contacted Nature to retract. She had found a serious flaw. Her method applied equally well to equations that are known not to have immortal solutions, which means it could not possibly be proving what she claimed. The mathematician Dean Yang observed that it is highly unlikely anyone can come up with a solution for the Navier-Stokes problem. Write it up and check it properly in less than a year. Smith had tried to do it in weeks. In 2014, Mukhtar-Bey Otelbayev, the director of the Mathematical Institute at Kazakhstan's Eurasian National University, published a 100-page proof in a regional journal. Within weeks, a counterexample to his main theorem was found, first by an anonymous user on a Russian mathematics forum, and then refined by Stephen Montgomery Smith and Terrence Tao. Otelbayev conceded publicly. "To my shame," he wrote, on page 56, "the inequality is incorrect. I am so sorry. 100 pages, a career's worth of reputation, undone by a single bad inequality on page 56. And just last year, a former director at Google DeepMind named David Budden wagered $45,000 across public bets that he could produce a formal computer-verified proof. His submission formalized a weaker or different version of the problem than the actual Millennium Prize statement. He paid out his bets in January. Observers called it a case study in what happens when AI systems produce mathematics that looks plausible but is not actually correct. So the equation was born from a wrong derivation, confirmed independently, adopted by all of engineering without proof of consistency, elevated to one of the 7 hardest problems in mathematics. And then every serious attempt to prove it as well behaved has crashed and burned publicly. That would be merely embarrassing, an intellectual curiosity, a mathematician's puzzle, if the equation had no practical consequences. But the Navier-Stokes equations are not a puzzle sitting in a journal. They are the foundation underneath your world. And the reason nobody can prove they work is connected to something that every physicist alive will admit is the single most important unsolved problem in all of classical physics. To understand why nobody can prove the Navier-Stokes equations behave, you need to understand the people who got closest, and you need to understand what happened to them when they tried. Because this is not a story of incremental progress toward a solution. It is a story of brilliant people pushing as far as human intelligence can go, and then hitting a wall that broke their methods, and in some cases, broke considerably more than that. 1934. A 28-year-old French mathematician named Jean Leray publishes a paper in Acta Mathematica that a Nature obituary would later describe as truly 40 years ahead of its time, and unsurpassed even today. The paper is called Sur le mouvement d'un liquide visqueux emplissant l'espace, on the motion of a viscous liquid filling space. What Leray was trying to do was straightforward. Prove that if you start the Navier-Stokes equations with smooth, reasonable initial conditions in 3 dimensions, the solution stays smooth for all time. No blow-up, no infinities. Just fluid doing what fluid does, described faithfully by the mathematics for as long as you care to compute. He could not do it. Nobody could. And Leray was arguably the most talented analyst of his generation. So instead of proving what he wanted to prove, he did something that would reshape mathematics. He invented a weaker notion of what it means to solve the equation. Instead of demanding that the solution be smooth at every point in space and time, he required only that it satisfy the equation in an averaged, integral sense when multiplied by smooth test functions and integrated over space. These are called weak solutions. They relax the requirements just enough that you can prove they exist. Think about what that means for a moment. The strongest mathematical result available in 1934, produced by one of the finest analysts alive, was essentially this: we cannot prove the real solutions exist. So here are some approximate ones that satisfy a weaker version of the equation, and we can at least prove those are there. Leray showed that these weak solutions exist globally for all time. He also showed that smooth solutions exist locally for some initial stretch of time. And he proved that if smooth solutions ever do break down, the set of times at which they break is vanishingly small, measure 0 in the technical sense. But he could not rule out the possibility of breakdown entirely. The gap between what Leray proved and what the Millennium Prize requires has defined the entire field for 90 years. And here is where Leray's story takes a turn that I think is one of the most remarkable in the history of mathematics. In 1940, Germany invaded France. Leray was a reserve officer. He was captured and spent the next 5 years as a prisoner of war at Oflag 17A, a camp for French officers in Edelbach, Austria. Now, Leray was one of the foremost experts in fluid dynamics in the world. He knew that if the German military discovered his expertise, they would almost certainly force him into weapons research. So he made a decision that would accidentally transform 20th century mathematics. He lied about his specialty. He told his captors he was a topologist, a mathematician who studies the abstract properties of shapes and spaces. He chose topology specifically because he believed it was the most useless field of mathematics imaginable from a military standpoint. Nobody was going to build a bomb with topology. And then, imprisoned in a camp with nothing but time, pretending to study a subject he had chosen for its uselessness, Jean Leray proceeded to invent two of the most important tools in all of modern mathematics: sheaf theory and spectral sequences. These are not minor contributions. They became foundational to algebraic topology and algebraic geometry. Henri Cartan, Jean-Pierre Serre, Armand Borel, and Alexander Grothendieck all built on Leray's wartime work to reshape entire fields. The man who spent his career trying to prove fluids behave, locked in a prison camp and pretending he studied shapes, accidentally revolutionized the mathematics of shapes instead. His collaborator was not as fortunate. Julius Schauder, a Polish-Jewish mathematician who had co-authored the landmark Leray-Schauder fixed-point theorem with Leray in 1934, was in Lvov when the Nazis arrived. Schauder was arrested by the Gestapo. He was never seen alive again. The exact date and circumstances of his death remain unknown. The Leray-Schauder theorem is still taught in every graduate mathematics program in the world. One of its creators survived the war by hiding his identity. The other was murdered because of his. I think about that sometimes. Two mathematicians working together in the early 1930s, producing a theorem about fixed points that would become one of the workhorses of nonlinear analysis, and then history breaks them apart. One invents a new branch of mathematics from a prison cell. The other disappears into the machinery of genocide. The theorem survives both of them, still carrying their names, still being used to study the very equations Leray could not fully tame. But Leray's weak solutions, his best contribution to the Navier-Stokes problem, had a flaw that would not be exposed for 85 years. Remember that. We will come back to it. While Leray was imprisoned in Austria, a girl was growing up in a small town in European Russia, whose life would intersect with the same equation in a way that is almost unbearably poignant. Olga Alexandrovna Ladyzhenskaya was born in 1922 in Kologriv, the youngest of three daughters of Alexander Ladyzhensky, a school principal and mathematics teacher descended from Russian nobility. Her father was the person who first taught her mathematics. He was also, by all accounts, a principled man who believed in education and refused to compromise with the increasingly paranoid Soviet bureaucracy. In October 1937, during Stalin's Great Purge, Alexander Ladyzhensky was arrested by the NKVD and declared an enemy of the people. Olga was 15 years old. As Alexander Solzhenitsyn later recounted, Ladyzhensky had been warned by a peasant in the village that his name was on the arrest list. He was urged to flee. He refused, saying his students depended on him. He is believed to have been tortured to death in an NKVD prison within a week of his arrest, sometime between October 23rd and October 30th. His body was never returned to the family. Every male member of the Ladyzhensky noble family who had not emigrated from Russia vanished during the purges and the war. Full rehabilitation, the Soviet government's formal admission that the charges were fabricated, did not come until 1956. Olga was 34 years old before the state admitted her father was innocent. As the daughter of an enemy of the people, Olga graduated high school with excellent marks, but was forbidden from entering Leningrad State University. The rejection was not academic, it was political. Her father's condemnation stained the entire family. She attended a provincial pedagogical institute instead, a teacher's training college far from the centers of mathematical life. After graduating, she returned to Collegrive and taught school at the same school where her father had been principal, the same school where he had taught mathematics before the NKVD took him. She taught, like her father had toward the end, without pay. It was not until 1943 that she was able to enter Moscow State University through the intervention of a sympathetic contact. She attended Israel Gelfan's first seminars. She was gifted, but she could not present her doctoral thesis until after Stalin died on March 5, 1953. Even then, her path was constrained by the political system at every turn. What she proved when she was finally allowed to work unimpeded was extraordinary. Between 1958 and 1959, Olga Ladyzhenskaya proved global existence and uniqueness of smooth solutions to the Navier-Stokes equations in 2 dimensions. The complete solution, the full answer to the question Leray had been unable to answer. In 2D, the equation is well behaved. Smooth initial conditions produce smooth solutions that exist for all time and never blow up. Case closed. After Stalin died, things slowly improved for Ladyzhenskaya, but the scars of her early life never fully healed. She moved to Leningrad, eventually becoming a professor at the Steklov Mathematical Institute, where she would work for the rest of her career. She married the mathematician Andrei Kiselev, though the marriage did not last. She never had children. Colleagues described her as fierce, passionate, and deeply principled. She was known for her physical vigor, her love of hiking and swimming, and her absolute refusal to tolerate mathematical sloppiness. She once told an interviewer that mathematics saved her life, that it gave her a world where justice existed, where a theorem was either true or false, where the arbitrary cruelty of political systems could not reach. The irony of her mathematical triumph is almost unbearable when you think about it in the context of her life. She proved that, in a 2-dimensional world, the Navier-Stokes equations are perfectly well behaved, orderly, just. Every smooth starting condition leads to a smooth solution forever. No blow-up, no catastrophe, no sudden violence emerging from calm beginnings. In 2 dimensions, the mathematical universe is fair. It follows its own rules. It does not betray you. But we live in 3 dimensions. And in 3 dimensions, the equation that she had mastered in its simpler form becomes something else entirely. In 3 dimensions, calm beginnings might lead to infinite violence. Smooth conditions might produce singularities. The mathematical universe stops being fair. It starts behaving, in a sense, like the political world she grew up in, where things that should not happen do happen, where forces amplify beyond all reason, where the rules seem to hold until suddenly they do not, and by then it is too late. I do not know if Ladyzhenskaya ever made that connection consciously. I do know she worked on the 3-dimensional problem for the rest of her life and never solved it. She died in 2004 at the age of 81. Her father was never mentioned in a single official Soviet mathematical biography published during her lifetime. The state that murdered him pretended he had never existed, even as his daughter became one of the most important mathematicians in Soviet history, but not in 3 dimensions. And the reason why is the single most important distinction in all of fluid dynamics. In 2 dimensions, the equation that describes how the spinning of the fluid, the vorticity, evolves over time is what mathematicians call a scalar transport diffusion equation. The vorticity can be carried around by the flow. It can be smeared out by viscosity, but it cannot be amplified. There is no mechanism in 2 dimensions for the fluid to take a vortex and make it spin faster. The spin stays bounded because the geometry of the plane does not allow for vortex stretching. In 3 dimensions, that changes completely. There is an additional term in the vorticity equation, the vortex stretching term. In 3 dimensions, the fluid can grab a tube-shaped vortex and stretch it longer and thinner, like pulling taffy. As the tube gets thinner, the vorticity concentrates into a smaller and smaller cross-section. And by conservation of angular momentum, it spins faster and faster and faster. There is nothing in the mathematics that guarantees this process stops. The vortex stretching term can amplify rotation without any upper bound that anyone has been able to prove. That single term is the source of everything. Every failed proof attempt, every retracted paper, every $1 million still sitting in the Clay Institute's accounts. Ladyzhenskaya killed the problem in 2 dimensions because vortex stretching does not exist there. In 3 dimensions, vortex stretching exists, and it defeated her the same way it defeated everyone else. Her monograph, The Mathematical Theory of Viscous Incompressible Flow, published in Russian in 1961 and translated into English in 1963, remains one of the foundational texts of the field. She was reportedly on the shortlist for the 1958 Fields Medal. When she and Leray finally met, after the Iron Curtain eased, they discovered they had been working on the same problems, independently, on opposite sides of a political divide for decades. So by the late 20th century, the situation was this. Leray had proved weak solutions exist, but could not prove they are smooth. Ladyzhenskaya had proved smooth solutions exist in 2D, but the method fails in 3D because of vortex stretching. The gap remained, and then 3 mathematicians decided to see how close they could get. In 1982, Luis Caffarelli, Robert Cohn, and Louis Nirenberg were walking through Chinatown in New York City when they decided to attack the Navier-Stokes regularity problem together. What they proved is the deepest result on Navier-Stokes singularities that anyone has achieved in the 43 years since, and it is still the state of the art today. Their paper established what is called partial regularity. They proved that the set of possible singularities in any suitable weak solution has one-dimensional parabolic Hausdorff measure, 0. In plain language, if singularities exist at all, if the solution does blow up somewhere, the set of points where it happens is vanishingly small. It cannot fill a curve in spacetime. It can be at most a scattering of isolated points. Singularities, if they are there, are almost invisible. But they could not rule them out. They proved singularities are rare if they exist. They could not prove they do not exist at all. The difference between those 2 statements is the difference between collecting $1 million and spending the rest of your career wondering. All 3 of those mathematicians went on to extraordinary careers. Caffarelli won the Abel Prize in 2023, the first South American-born laureate. Nirenberg shared the Abel Prize in 2015 with John Nash. Cohn died in January 2016 after a long battle with cancer, and their result from that conversation in Chinatown remains the best anyone has done. But here is where it gets worse. Remember Leray's weak solutions, the fallback position that the entire field had relied on since 1934. In 2019, Tristan Buckmaster and Vlad Vikol published a paper in the Annals of Mathematics proving that weak solutions to the 3-dimensional Navier-Stokes equations are not unique. They proved you can have multiple different weak solutions starting from the same initial conditions. This destroys the classical strategy that mathematicians had been hoping might work for nearly a century. The idea was always that you would construct weak solutions the way Leray did, and then prove that all weak solutions must actually be smooth. But if weak solutions are not unique, if you can get different answers from the same starting point, then showing one of them is smooth tells you nothing about the others. The entire approach collapses. So Leray's path is dead. Ladyzhenskaya's method only works in 2D. Caffarelli-Cohn-Nirenberg got closer than anyone, but could not close the gap. And the classical strategy for connecting weak solutions to smooth solutions was killed in 2019. Every major approach that the 20th century produced has been tried and has failed. And the reason they all failed, the common thread connecting every one of these brilliant failures, has a name that physicists have been dreading for 150 years: turbulence. The word sounds almost mundane. You have felt it on an airplane. You have watched it in a river, running over rocks. Smoke rising from a candle tip breaks into turbulence within inches. It seems ordinary. It is the single most important unsolved problem in classical physics, and every great physicist who has confronted it has admitted defeat. The quote you will see attributed to Werner Heisenberg most often goes something like this: "When I meet God, I am going to ask him two questions. Why relativity and why turbulence? I really believe he will have an answer for the first." It is a great quote. It is also almost certainly something Heisenberg never actually said. No primary source for it has ever been found, and the same line has been attributed to at least 3 different physicists over the decades. What is true is that Heisenberg's doctoral thesis in 1923, supervised by Arnold Sommerfeld, was on the stability of laminar flow, which is the smooth, orderly type of fluid motion that exists before turbulence takes over. Sommerfeld later admitted that he would not have proposed a topic of this difficulty to any of his other students. The young Heisenberg struggled with it. Everyone struggles with it. The thesis was adequate. The problem was not solved. The quote that is reliably sourced comes from Horace Lamb, the British mathematician whose textbook Hydrodynamics was the definitive reference on fluid dynamics for half a century. In 1932, at a meeting of the British Association for the Advancement of Science, Lamb was 82 years old. He said that when he died and went to heaven, there were 2 matters on which he hoped for enlightenment. One was quantum electrodynamics, and the other was the turbulent motion of fluids. About the former, he said, he was rather optimistic. He was not making a joke about how hard quantum electrodynamics is. He was making a joke about how hard turbulence is. He was saying that he expected God could explain quantum electrodynamics, but turbulence might defeat even the Almighty. And this was not some offhand remark on his deathbed, by the way. He lived 2 more years. He said it at a formal scientific gathering in front of his peers and meant every word of it. Richard Feynman said it most directly. In Volume 1 of the Feynman Lectures on Physics, published in 1963, he wrote that there is a physical problem common to many fields that is very old and that has not been solved. Nobody in physics has really been able to analyze it mathematically satisfactorily, in spite of its importance. It is the analysis of circulating or turbulent fluids. That sentence has been condensed over the years to turbulence is the most important unsolved problem of classical physics. The condensed version is a faithful paraphrase, and it remains true today. So, what is turbulence exactly? And why does it connect to the Navier-Stokes problem in a way that makes both problems feel hopeless? The transition from smooth to turbulent flow was first demonstrated visually by Osborne Reynolds in 1883 at the Royal Society. He was meticulous about the setup. A glass pipe about 1 inch in diameter and several feet long, mounted in a large tank of water that had been left to settle overnight so there were no residual currents. A thin stream of dye injected through a fine nozzle at the center of the pipe entrance. At low flow rates, the dye traced a thread so clean and straight that it looked painted onto the glass. You could see individual layers of fluid sliding over each other like sheets of paper in a stack. That is laminar flow. It is beautiful and orderly, and it obeys the equations without complaint. Then Reynolds opened the valve a little more, and a little more. At a certain point, the thread began to oscillate. Small waves appeared, and then, as if someone had flipped a switch, the thread exploded into a cloud of color that filled the entire pipe. The transition was violent and sudden. One moment, order. The next, chaos. Reynolds recorded the critical velocity at which this happened for different pipe diameters and different fluids, and found that the transition always occurred at the same value of a single dimensionless number, now called the Reynolds number. It is the ratio of inertial forces to viscous forces in the fluid, calculated as the flow velocity times a characteristic length divided by the kinematic viscosity. For pipe flow, the critical threshold is approximately 2300. Below that number, viscosity dominates and the flow stays smooth. Above it, inertial forces overpower viscosity and chaos takes over. It did not matter what fluid you used, what size pipe, what velocity. If the Reynolds number crossed that threshold, turbulence was inevitable. The universe seemed to have a built-in toggle between order and chaos, and the Reynolds number was the switch. Richardson, the man who gave us the cascade, deserves more of this story than he usually gets. He was born in 1881 into a Quaker family in Newcastle, and his pacifism was not theoretical. When the First World War broke out, he refused to fight, but volunteered as an ambulance driver with the Friends ambulance unit attached to the French army. He served at the front, carrying wounded soldiers out of the trenches at Ypres and Champagne. He was awarded the French Croix de Guerre for bravery. And while he was driving ambulances through the mud and blood of the Western Front, he was also doing mathematics, literally doing calculations on the battlefield. He was working out the first ever numerical weather prediction, solving the atmospheric equations by hand, using data from a single 6-hour observation period on May 20th, 1910. The calculation took him 6 weeks. The result was catastrophically wrong, predicting a pressure change 100 times larger than what actually occurred. He published the result anyway, honestly, in his 1922 book, noting the discrepancy and analyzing what went wrong. The error, it turned out, was caused by unsmoothed initial data, essentially the same problem of sharp gradients that plagues Navier-Stokes to this day. Richardson's failure was ahead of its time in the same way Leray's success was ahead of its time. In that same book, Richardson gave the energy cascade its most enduring description. He wrote it as a little verse. Big whirls have little whirls that feed on their velocity, and little whirls have lesser whirls, and so on to viscosity. It was a playful riff on a Jonathan Swift poem about fleas, but it captures the essential physics perfectly. Energy enters a turbulent flow at large scales in the form of big eddies. Those large eddies become unstable and break into smaller eddies. The smaller eddies break into smaller ones still, and so on, through a cascade of ever-decreasing scales until the eddies are small enough that viscosity can finally dissipate their energy as heat. His forecast factory thought experiment, the giant hall with 64,000 human computers, was not just a flight of fancy. He worked out the logistics in detail, how many computers would be needed for each region, what communication links they would require, how the conductor on the central pillar would synchronize their calculations. It reads like science fiction, but the math was serious, and the vision became reality decades later when electronic computers replaced his imaginary army of human calculators. Richardson lived to see the first successful numerical weather prediction made by a team using ENIAC in 1950, 30 years after his failed attempt. The vindication must have been bittersweet. His idea was right. His technology was 30 years too early. After the war, Richardson became increasingly focused on the mathematics of conflict. He developed mathematical models of arms races and the statistical properties of wars, essentially found in the field of mathematical peace research. He died in 1953, the same year as Stalin, though the two deaths had rather different consequences for the world. Kolmogorov, who made Richardson's turbulence intuition rigorous, lived one of the most productive mathematical lives in history. Born in 1903 in Tambov, Russia, he was raised by his aunts after his mother died giving birth to him. His father was an agronomist who was largely absent. By the age of 5, he had noticed patterns in the sums of odd numbers and was publishing findings in his aunt's local newsletter. He entered Moscow State University at 17 and never left, spending his entire career there. His contributions span probability theory, topology, mathematical logic, information theory, algorithmic complexity, and of course, turbulence. He is one of perhaps a dozen mathematicians in history whose work fundamentally shaped multiple unrelated fields. His 1941 turbulence theory rests on a single bold assumption called the local isotropy hypothesis. At sufficiently small scales, far from the boundaries and far from the energy-containing eddies, turbulence forgets where it came from. The statistics of the small eddies become isotropic, meaning the same in all directions, and universal, meaning the same regardless of how the turbulence was generated. Whether the flow is a jet engine exhaust, or a waterfall, or a hurricane, at the smallest scales, turbulence looks the same. And from this assumption falls the 5/3 power law, which has been confirmed by measurements in an extraordinary range of natural and laboratory flows. But Kolmogorov's theory is statistical. It tells you about averages and spectra and probability distributions. It does not tell you about individual flow events. It does not tell you whether at some specific point in space and time the velocity might become infinite. It describes what turbulence looks like on average, without answering whether the individual events that make up that average are always finite. The distinction matters because the Millennium Prize problem is not asking about averages. It is asking about the worst case. It is asking whether there exists even a single starting condition among all possible starting conditions that leads to infinity. And the computational reality of turbulence makes the problem feel even more hopeless. I mentioned that direct numerical simulation of atmospheric turbulence would require roughly 10 to the 20th grid points. Let me put that in perspective. The fastest supercomputer on Earth, as of 2025, can perform roughly 1.5 exaflops, which is about 1.5 times 10 to the 18 floating point operations per second, to simulate 1 second of atmospheric turbulence directly. Resolving every scale from the 10-meter energy-containing eddies down to the 1-millimeter Kolmogorov microscale would take that computer longer than the current age of the universe. We are not talking about a hard computation. We are talking about a computation that is physically impossible on any computer that could conceivably be built from the matter in our solar system. And that means we cannot just run the equation and see what happens. We cannot brute force the answer. We cannot simulate our way out of the problem. The only path to the answer is pure mathematics, proof. And after 90 years, proof has not come. And here is where I need to correct a misconception that is important, because it feeds directly into why the Navier-Stokes problem is so hard. Turbulence is not random. I know it looks random. When you watch smoke dissipate into the air or white water churn in a river, it appears disordered, unpatterned, chaotic in the colloquial sense, but it is not random in the mathematical sense. Turbulence is entirely deterministic. Every swirl, every eddy, every seemingly chaotic fluctuation is governed precisely by the Navier-Stokes equations. If you could specify the initial conditions with perfect precision, and if you had infinite computational power, you could predict every detail of a turbulent flow. The unpredictability comes from extreme sensitivity to initial conditions, the hallmark of deterministic chaos, not from any inherent randomness in the physics. And here is the connection to the Navier-Stokes blow-up problem that I think is not discussed enough. The energy cascade in turbulence is moving energy from large scales to small scales. The vortex stretching term in 3 dimensions is concentrating vorticity into smaller and smaller regions. These are the same process. Turbulence is what vortex stretching looks like when it happens everywhere in the flow at once. The mathematical difficulty, the question of whether the Navier-Stokes equations blow up, is really a question about whether the turbulent cascade can concentrate energy into an infinitely small region, infinitely fast. Whether the process of big whirls breaking into little whirls can go all the way down, past the Kolmogorov microscale, past any finite scale, to a point where the velocity becomes infinite. In a real fluid, that does not happen. At some sufficiently small scale, the continuum model of fluids breaks down, and you have to think about individual molecules. You cannot have a vortex smaller than the mean free path of the molecules. Physics imposes a natural cutoff, but the Navier-Stokes equations do not know about molecules. They treat the fluid as a continuous substance, infinitely divisible, all the way down. And the question is whether the mathematics, freed from the physical cutoff that molecules provide, can produce an infinity. I want you to hold that image in your mind. The turbulent cascade, energy spiraling down through ever smaller scales. The equations say nothing stops it. The physics seems to stop it, but not because the equations guarantee it. Something else is happening. Something in the real world that the math does not capture. And the question of what that something is, and whether it always works, is not just an abstract puzzle. It is connected to a result from the greatest living mathematician that took the entire field by surprise. Because in 2014, Terrence Tao stopped asking whether the equations blow up and started asking what it would look like if they did. And what he found was something nobody expected. He found that you could build a computer out of water. And that computer, if it could be made to work within the actual Navier-Stokes equations, would blow up on purpose. Terrence Tao is not easy to describe without sounding like you're exaggerating. He was born on July 17, 1975, in Adelaide, Australia, to parents who had emigrated from Hong Kong. By the age of 2, he was teaching 5-year-olds to spell and add. He scored 760 on the mathematics section of the SAT at the age of 8, not the test for 8-year-olds, the SAT, the college admissions exam. At 8 years old, he scored higher than most high school seniors. His record at the International Mathematical Olympiad remains unmatched in the history of the competition. Bronze medal at age 10, silver at 11, gold at 12. He is the youngest winner of each level of medal a competition has ever seen, and no one has beaten those records in the decades since. He completed his PhD at Princeton under Elias Stein at the age of 20 He joined the faculty at UCLA and became the university's youngest full professor in its history at 24. When Paul Erdos, one of the most prolific mathematicians of the 20th century, wrote a recommendation letter for the young Tao, he predicted simply that he was sure Tao would develop into a first-rate mathematician, and perhaps into a really great one. Erdos was understating it. Tao won the Fields Medal in 2006. He won the Breakthrough Prize in Mathematics in 2014, which came with $3 million. He has won a MacArthur Fellowship, the Crayford Prize, the Royal Medal, and so many other honors that listing them feels redundant. Charles Pfefferman, the Princeton mathematician who wrote the official Millennium Prize statement for the Navier-Stokes problem, once said that if you are stuck on a problem, one way out is to interest Terrence Tao. The implication being that there are very few problems in mathematics that Tao cannot make progress on if he decides to focus. His mathematical blog, called What's New, is one of the most widely read mathematical communication platforms in existence. The American Mathematical Society has published multiple volumes collecting his blog posts as books. He communicates openly about his work in progress, his failed approaches, and his intuitions about unsolved problems. This matters for our story because it means we know, from Tao's own words, exactly what he thinks about Navier-Stokes. On February 3rd, 2014, Tao uploaded a paper to the ArcSiv preprint server. The title was Finite Time Blowup for an Averaged Three-Dimensional Navier-Stokes Equation. The paper was published 2 years later in the Journal of the American Mathematical Society, one of the most prestigious journals in the field, and what it proved changed the way the entire mathematical community thinks about the Navier-Stokes problem. Here is what Tao did. He took the Navier-Stokes equation and replaced the specific nonlinear term, the part that describes how the fluid carries its own velocity, with an averaged version. He averaged the nonlinearity using spatial rotations, dilations, and Fourier multipliers of order 0. The technical details matter less than the key property. His averaged nonlinear term still satisfies the energy identity. That is, the averaged equation conserves energy in exactly the same way the real Navier-Stokes equation does. In terms of every abstract mathematical property that anyone had ever used to study the Navier-Stokes equations, Tao's averaged version is indistinguishable from the real thing. It satisfies the same function space estimates. It obeys the same conservation law. From the perspective of every tool in the mathematician's toolkit, it looks the same. And Tao proved that it blows up. Smooth solutions to his averaged equation become infinite in finite time. Not a conjecture, not a heuristic argument, not a numerical simulation suggesting blow-up. A rigorous mathematical proof checked by the referees of one of the most demanding journals in mathematics, confirmed and published. The implication is devastating, and I want to be precise about what it does and does not mean. It does not prove that the real Navier-Stokes equations blow up. Tao's averaged equation is not the real equation. The averaging changes the specific geometric structure of the nonlinearity, and it is conceivable that the real nonlinearity has special properties that prevent blow-up, even though the averaged version does not. But what the result does prove is this. Any proof that the real Navier-Stokes equations are well-behaved, any proof that smooth solutions exist for all time, that relies solely on the energy identity and abstract function space estimates on the nonlinearity, is guaranteed to fail because those same tools apply equally to Tao's averaged equation. And Tao's equation blows up. The tools cannot distinguish between an equation that behaves and one that explodes. Any successful proof must therefore use something specific about the real Navier-Stokes nonlinearity, some fine structural property that distinguishes it from its averaged cousins. And nobody knows what that property might be. This is what mathematicians call the supercriticality barrier. It means the problem is harder than the tools, the standard methods of partial differential equations, the energy estimates, and Sobolev inequalities, and all the machinery that the field has developed over a century are not enough. Something fundamentally new is required, which is exactly what Charles Fefferman said in 2000 when he wrote the problem statement. We probably need some deep, new ideas. Tao's result proved he was right in the most concrete possible way. But the way Tao achieved the blow-up is the part that I have not been able to stop thinking about since I first read his paper. Because it was not some abstract trick, it was an engineering project. Tao described his construction as building logic gates out of fluid. Think about what that means. A logic gate in a computer is a physical device that takes input signals and produces output signals according to a fixed rule. An AND gate outputs 1 only if both inputs are 1. An OR gate outputs 1 if either input is 1. You can build any computation out of these basic components. Every computer you have ever used is, at the deepest level, just a vast network of logic gates. What Tao imagined and then proved could exist within the mathematics of his averaged equation was the same kind of construction made out of fluid, energy pumps that move kinetic energy from one scale to another, threshold-activated switches where energy at a certain scale triggers a cascade at a smaller scale once a critical level is reached. And then these components wired together into a self-replicating machine. The machine makes a copy of itself at a smaller scale. That copy runs faster because it is smaller. It makes another copy at an even smaller scale. That copy runs even faster, each generation concentrating more energy into a tinier region of space, operating at higher and higher frequencies, until the process reaches infinite speed in an infinitely small space, and the solution blows up. He compared it to Conway's Game of Life, the cellular automaton, where simple rules about which cells on a grid live and die can produce extraordinarily complex behavior. People have built functioning computers, self-replicating machines, and universal constructors entirely within the rules of that game. Tao was proposing the same thing for fluid dynamics. Build a computer out of water. Program it to replicate itself at smaller and smaller scales, and watch it blow up. In a public lecture at Yale, he framed it in the most vivid terms. Imagine that someone awfully clever could construct a machine out of pure water, not built from rods and gears, but from a pattern of interacting currents. And imagine this machine were able to make a smaller, faster copy of itself, which could then make another, and so on, until one has infinite speed in a tiny space and blows up. Then he added with a laugh that he did not know how to actually build such a machine within the real Navier-Stokes equations, only within his averaged version. But on his blog, he was more explicit about what he believed. He wrote that the method of proof hints at a possible route to establishing blow-up for the true Navier-Stokes equations, and that he was now increasingly inclined to believe that blow-up is the case for the real equations, albeit for a very small set of initial data. That sentence, from one of the most careful and precise mathematical communicators alive, is as close to a prediction as you will get from someone of Tao's stature. He thinks the equations blow up. He thinks, somewhere in the infinite space of possible initial conditions, there exist configurations of fluid that will produce infinite velocities in finite time within the Navier-Stokes framework. What makes Tao unusual among mathematicians of his stature is his openness. Most Fields medalists, most people at the absolute peak of mathematical achievement, are guarded about their work in progress and cautious about stating opinions on unsolved problems. Tao is not. He blogs about ideas that might not work. He publicly discusses his intuitions about problems he has not solved. He posts informal notes and half-formed conjectures alongside his polished theorems. This makes him an unusually reliable source for understanding what the best mathematicians actually think about Navier-Stokes, as opposed to what they are willing to put in a peer-reviewed paper. And what Tao thinks is that the equations probably blow up. He has been careful to qualify this. He says it would happen for a very small set of initial data. He says he does not know how to prove it for the real equations as opposed to his averaged version. He says it is an inclination, not a claim, but the inclination of the mathematician that other mathematicians call, when they are stuck, carries a weight that goes beyond a casual opinion. When Tao says he increasingly believes blow-up occurs, the mathematical community listens. The Chen and Ho result from 2022 sharpened this considerably. To understand why their proof matters, you need to understand the relationship between the Euler equations and the Navier-Stokes equations. The Euler equations are what you get when you set viscosity to 0. No internal friction at all, pure transport and pressure. The Euler equations describe an idealized fluid that slips past itself without any resistance. In the real world, no fluid is perfectly inviscid, but at high Reynolds numbers, the viscous effects are tiny compared to the transport, and the Euler equations become a good approximation. For more than 250 years, mathematicians could not determine whether the three-dimensional Euler equations blow up. Chen and Hu settled it. They identified a specific type of initial condition, an axisymmetric flow with a particular vortex configuration, and proved rigorously that the solution develops a singularity in finite time. The velocity becomes infinite. The proof used a computer-assisted approach, combining analytical estimates with rigorous numerical verification, and was published in the Proceedings of the National Academy of Sciences. The significance for Navier-Stokes is direct. If the inviscid equation blows up, then the question for the viscous equation is whether viscosity is strong enough to prevent the blow-up that would otherwise occur. In the averaged equation, Tao showed it is not. Viscosity cannot stop the blow-up. In the real equation, the question is open, but the fact that both the averaged equation and the inviscid equation blow up means the real equation is surrounded on two sides by equations that fail. It is sandwiched between blow-up on the left and blow-up on the right, and the only question is whether it is narrow enough to thread the needle. That is not a comforting position to be in. Hu's statement that he has identified a promising blow-up candidate for the full Navier-Stokes equations with viscosity should not be taken lightly. Hu is not a self-promoter. He spent decades carefully studying the problem before making his Euler breakthrough. If he says he has a candidate, the community takes it seriously. And if his program succeeds, the implications cascade through every field that depends on the equations. It would not mean that aircraft would fall out of the sky. The blow-up initial conditions, if they exist, would almost certainly be exotic, artificial configurations that never arise in practical engineering. But it would mean that the equation underlying all of computational fluid dynamics is mathematically inconsistent in the general case. It would mean that the framework is not airtight. It would mean that we got lucky in a sense, that the practical applications happen to avoid the bad configurations. And it would mean that no mathematical guarantee can ever be given that a fluid simulation will not encounter one of those configurations, even if the probability is vanishingly small. That is not the kind of uncertainty that engineers are accustomed to. Engineers work with safety factors and failure modes and probability distributions. They are comfortable with uncertainty about specific values. They are not comfortable with uncertainty about whether the fundamental equations they use are logically consistent. That is a different kind of uncertainty entirely, and nobody has seriously thought through what it would mean for engineering practice if the answer turned out to be no. He described the mechanism in a piece for Nature Reviews Physics in 2019 as a Maxwell's demon inside the fluid. Maxwell's demon is a famous thought experiment in thermodynamics, a hypothetical being that sorts fast and slow molecules to create order from disorder, seemingly violating the second law of thermodynamics. Tao's fluid demon is analogous. It is a mechanism within the flow itself that keeps pushing energy to smaller and smaller scales, defeating viscosity's attempt to dissipate it, until the cascade reaches a singularity. On the Lex Fridman podcast, he explained it more simply. The dissipation force coming from viscosity is very well understood. It is linear. It calms things down. If viscosity was all there was, then nothing bad would ever happen. But there is also transport. Energy from one location of space can get transported because the fluid is in motion to other locations. And that is a non-linear effect. And that causes all the problems. Transport versus dissipation. Chaos versus calm. The fluid carrying energy to smaller scales faster than viscosity can dissipate it. That is the fundamental competition at the heart of both the Navier-Stokes problem and the turbulence problem. Tao showed that in a universe where the nonlinearity is slightly smeared out, chaos wins. The question is whether chaos can win in our universe too. But even Chen and Ho's result is not the most unsettling part of this story, because in July 2005, a result was published that I genuinely believe should have been front-page news and was not. A team of mathematicians proved that steady solutions to the viscous Navier-Stokes equations can be Turing complete. I need to explain what that means, because if you understand it, the ground shifts. A system is Turing complete if it can simulate any computation that any computer, any theoretical computing device could ever perform. Your laptop is Turing complete. Conway's game of life is Turing complete. And now we know that certain fluid flows described by the Navier-Stokes equations are Turing complete. The equations do not just describe how fluid moves, they can compute. Certain arrangements of fluid, certain steady-state solutions to the Navier-Stokes equations can perform any algorithmic task, calculate pi, run a chess engine, simulate another universe. And here is why that matters for the question of whether the equations are provably reliable. One of the foundational results in mathematical logic, proved by Alan Turing in 1936, is that there exist properties of Turing-complete systems that are undecidable. Undecidable does not mean unsolved. It does not mean we have not found the answer yet. It means there is no algorithm, no proof procedure, no finite method that can answer the question in every case. The halting problem is the most famous example. There is no general procedure that can determine for every possible computer program whether that program will eventually stop or run forever. And if the Navier-Stokes equations can simulate any computer program, then certain questions about the behavior of Navier-Stokes solutions may be similarly undecidable. This does not prove that the specific Millennium Prize question is undecidable. The existence and smoothness problem is a specific, precisely formulated mathematical statement, and it may well have a definite proof or disproof. But the Turing completeness result tells us that the Navier-Stokes equations are computationally rich enough to encode undecidable problems. The equation is not just describing fluid, It is computing, and some of its computations may be beyond the reach of any proof. Remember the first foreshadow back in the opening. Some mathematicians now suspect the problem might be fundamentally unsolvable. This is what they mean. Not that humans are too stupid, but that the equation itself might contain behaviors that sit beyond the boundary of what mathematical proof can characterize. The equation is too rich, too expressive. It can do too much. And civilization built everything on top of it anyway. So here is where we are. The equation was derived 200 years ago by a man whose own bridge collapsed. The best mathematicians of the 20th century threw everything they had at it and could not prove it behaves. The weak solution approach that sustained the field for 85 years was shown to be fundamentally flawed in 2019. The greatest living mathematician has demonstrated that a version of the equation, indistinguishable from the real thing by every known analytical tool, blows up in finite time. The inviscid version has been rigorously proven to blow up, and the equation itself has been shown to be computationally capable enough that certain questions about its behavior may be formally undecidable. That would be a remarkable intellectual story if it ended there. An unsolved math problem, a philosophical curiosity about the limits of proof, something for mathematicians to argue about at conferences. But it does not end there, because this equation is not sitting in a journal collecting dust. It is holding up your world. I want to walk you through what that actually means, concretely, with numbers, because I think the scale of our dependence on this single set of unproven equations is something that most people have never been confronted with. And confronting it changes how you feel about the word unproven. Start with the air. Right now, as you are reading this, the European Centre for Medium-Range Weather Forecasts is running the most accurate weather prediction system on Earth. Their operational model divides the atmosphere into a three-dimensional grid. At research resolution, that grid has 256.8 million grid points per vertical level, with well over 100 vertical levels stretching from the surface to the stratosphere. The horizontal spacing is 9 kilometers. Every single one of those grid points is updating 4 times a day by solving the Navier-Stokes equations for the motion of the atmosphere at that location, accounting for temperature, humidity, pressure, wind speed, and the interactions with neighboring grid points. The system runs on 4 Atos Bull-Sequana supercomputer clusters, delivering 30 petaflops of processing power, purchased under an €80 million contract. It is one of the largest civilian supercomputing operations on the planet, and its sole purpose is to solve the Navier-Stokes equations fast enough to predict the weather before the weather actually happens. The American system, NOAA's Global Forecast System, runs at 13-kilometer resolution, with 127 vertical layers, producing 16-day forecasts 4 times daily on supercomputers, delivering 5.78 petaflops. 50 years ago, weather predictions beyond a single day were, in the words of researchers at the time, of dubious utility. Today, forecasts are reliable out to roughly a week, with skill improving by approximately 1 day per decade. That improvement is driven almost entirely by finer grid resolution and better numerical methods for solving the Navier-Stokes equations. Every hurricane evacuation order, every airline flight rerouted around a storm, every frost warning that saves a crop traces back to a computer solving equations that nobody can prove always produce sensible answers. Now the air in a different sense. Every commercial aircraft flying today was designed with computational fluid dynamics playing a central role. The shift from physical testing to simulation has been one of the most consequential technological transitions of the last 50 years. Boeing's progression tells the story in a single comparison. The 767, introduced in 1982, required 77 wind tunnel tests during development. The 787 Dreamliner, certified in 2011, required 11. The other 66 tests were replaced by computers solving the Navier-Stokes equations. The Dreamliner burns 20% less fuel than comparable aircraft, a combined effect of aerodynamic optimization through CFD, composite materials, and advanced engine design, per Stanford professor Anthony Jameson, one of the pioneers of computational aerodynamics. A 5% improvement in lift-to-drag ratio translates to $5 billion in fuel savings for a fleet of 500 aircraft over 25 years. Those efficiency gains come directly from the fidelity of Navier-Stokes simulations. Airbus followed the same trajectory. The A350 and A380 were both developed with CFD as a primary design tool. Military aircraft are even more dependent. The F-35 Lightning II used high-fidelity Navier-Stokes simulations extensively for its stealth-optimized airframe, where the precise behavior of air flowing over angular surfaces at various speeds and angles of attack is critical to radar cross-section performance. Rocket nozzles, helicopter rotors, wind turbine blades, the aerodynamics of high-speed trains, all designed with the same unproven equations. And the software that does this is not a small industry. The global computational fluid dynamics software market was valued at approximately $2.4 to $2.65 billion in 2024 and is projected to reach $4 to $5 billion by 2030. The major vendors are Ensys, Siemens with their Star CCM Plus platform, and Dassault Systèmes. But the market size understates the economic footprint because it only captures the software licenses. It does not capture the value of the aircraft, bridges, buildings, vehicles, and infrastructure designed using that software. The broader engineering simulation market, of which CFD is a substantial component, stands at roughly $20 billion. The actual value of physical infrastructure whose design depended on Navier-Stokes simulations is incalculable. It is, in a meaningful sense, all of it. Now, consider the human body. Patient-specific computational fluid dynamics for cerebral aneurysms, where a simulation solves the Navier-Stokes equations with blood modeled as an incompressible Newtonian fluid with a density of 1,056 kilograms per cubic meter and a viscosity of 0.0035 Pascal seconds, was first reported in 2003. By 2024, these simulations had achieved an area under the receiver operating characteristic curve of 0.86 for predicting treatment outcomes. That is a strong predictive accuracy. Surgeons are making decisions about whether and how to operate on blood vessels in the human brain based on simulations of fluid dynamics that depend on unproven equations. Healthcare CFD simulations grew by approximately 30% in 2024 alone. During the COVID-19 pandemic, Navier-Stokes-based CFD was used worldwide to model how respiratory droplets and aerosols move through indoor spaces. One study found that increasing ventilation from 2.0 to 5.6 air changes per hour decreased aerosol concentration by a factor of 2.8. Those findings influenced hospital ventilation guidelines, school reopening policies, and office building design standards. Public health decisions affecting hundreds of millions of people were made on the basis of unproven equations describing how air moves through rooms. And the consequences of getting fluid dynamics wrong are not hypothetical. They are historical. The Tacoma Narrows collapse is worth lingering on because it illustrates something specific about what happens when fluid dynamics is not properly understood, and because the usual telling of the story gets the physics wrong. You will see it described in textbooks as a resonance failure, where the wind frequency matched the bridge's natural frequency and amplified the oscillations. That is not what happened. The actual mechanism was aeroelastic flutter, a self-excited instability where the motion of the bridge changes the aerodynamic forces acting on it, which changes the motion, which changes the forces, in a feedback loop that draws energy from the wind. It is the same physics that makes a flag ripple, that makes telephone wires hum, that makes certain road signs vibrate in a crosswind. It is a Navier-Stokes problem, through and through. The air moving over the bridge deck created vortices that shed alternately from the upper and lower surfaces, and the deck's own oscillation influenced the timing and strength of those vortices in a way that amplified the motion rather than damping it. The engineers who designed the bridge were not incompetent. They were working with the tools available in 1938. Wind tunnel testing of bridge sections was not standard practice. The aeroelastic coupling between a flexible structure and a turbulent airflow was not well understood theoretically. The failure catalyzed an entire field. After Tacoma Narrows, every major suspension bridge design in the United States was required to undergo wind tunnel testing, and the field of computational wind engineering was born. Which is to say, the field of solving Navier-Stokes equations around bridges. Deepwater Horizon is a different kind of lesson. The explosion itself was a drilling failure, a blowout caused by a series of decisions and oversights that had nothing to do with fluid dynamics equations. But the aftermath, the 97 days of oil flowing into the Gulf of Mexico, was entirely a Navier-Stokes problem. Where would the oil go? How deep would it penetrate? Which coastlines were at risk? How would the dispersants interact with the ocean currents? All of these questions were answered by numerical models solving the Navier-Stokes equations for ocean circulation, coupled with transport models for the oil itself. The models were imperfect. They disagreed with each other. They were updated and recalibrated as new data came in. But they were the only tools available, and billion-dollar response decisions depended on them. $8.8 billion in natural resource damage settlements, 11 lives lost. And the mathematical tools used to manage the disaster were the same unproven equations we have been discussing. There is an interesting psychology at work in the engineering profession's relationship with Navier-Stokes. Engineers know the equations are unproven. It is not a secret. Any aerospace engineer or fluid dynamicist who has taken a graduate-level course knows about the Millennium Prize Problem. They know the existence and smoothness question is open, and they do not care, not because they are reckless, but because the engineering mindset is fundamentally different from the mathematical mindset. A mathematician needs proof. A mathematician cannot say the equations work until the equations are proven to work. An engineer needs evidence, and the evidence is overwhelming. Decades of validated simulations, thousands of aircraft designed and flown, millions of weather forecasts verified against observations. The engineering community has a century of empirical evidence that the equations produce reliable results within the operating ranges that matter for practical applications. The gap between mathematical proof and engineering confidence is real, and for practical purposes, the engineers are right to rely on the equations. Nothing in their experience suggests the equations are unreliable. Nothing in any practical application has ever produced a result consistent with blow-up. The mathematical abstraction might have creases in it, but the physical territory the engineers are walking on is flat. So they walk, and the bridges stand, and the planes fly, But the question that nags, the question that this entire story circles back to, is whether the flatness of the territory is guaranteed or merely observed, whether the safety of the map is a mathematical certainty or a lucky streak, whether the engineers are right because the physics is right, or whether the engineers are right because the physics has not yet handed them one of the exotic initial conditions that Tao believes would break the math. And that question, the question of luck versus law, is the question that no one can answer, because answering it requires the very proof that nobody can produce. Wind energy. DNV, one of the largest classification and certification companies in the world, has delivered CFD analyses for over 1,000 wind farm projects globally. The placement of every turbine in those farms, the spacing between them, the prediction of how wake effects from upwind turbines reduce the power output of downwind ones. All of that depends on Navier-Stokes simulations run on meshes of 30 million cells or more. The global wind energy market represents hundreds of billions of dollars of installed capacity, all positioned according to fluid dynamics simulations based on unproven mathematics. Formula One, as I mentioned earlier, caps teams at 30 teraflops of CFD computation per testing period. This regulation exists because the teams demonstrated that CFD, meaning Navier-Stokes solutions, had become so accurate that it was more efficient than physical wind tunnel testing for most development tasks. The regulations essentially acknowledge that solving unproven equations in a computer is now more reliable than physical experiments with real air. Pause on that. The sport's governing body recognized that simulating reality using an equation nobody can prove is consistent produces better results than measuring reality directly. Automotive design. Every modern car undergoes extensive CFD analysis for aerodynamic drag, cooling airflow, and cabin ventilation. The aerodynamic optimization of vehicle shapes to reduce fuel consumption and wind noise is a Navier-Stokes problem. Urban planning. Building codes in high wind zones depend on computational wind engineering studies that solve the Navier-Stokes equations around proposed structures to predict wind loads on facades, pedestrian-level comfort, and snowdrift patterns. Nuclear safety. The cooling systems of nuclear reactors are analyzed using CFD to ensure adequate heat removal under normal and emergency conditions. The regulatory approval of reactor designs includes Navier-Stokes-based simulation results. I am going to stop listing examples because I could continue for hours and the point is already made. The point is not that the Navier-Stokes equations are used in many places. The point is that they are used in every place where fluid moves and human welfare depends on predicting how. There is no backup equation. There is no alternative mathematical framework waiting in the wings in case Navier-Stokes turns out to be unreliable. If these equations are fundamentally flawed in some way that we have not yet encountered in practice, there is nothing to fall back on. And yet, somehow, everything works. Planes fly, storms are forecast, blood flows through simulated arteries, and surgeons cut based on what the simulations tell them. Bridges stand, turbines turn, reactors cool. The equation delivers. Year after year, decade after decade, across every engineering discipline on the planet. Which brings us to the question that I think is the real question. The question that keeps me up if I think about it for too long. Not whether the equation can be proven, but why it works when it has not been proven. What is it about the physical world that makes the equation reliable, even though the mathematics permits catastrophe? Because Tao showed that the averaged equation blows up. Chen and Ho showed the inviscid version blows up. The mathematical landscape around the Navier-Stokes equations is littered with blow-up results for equations that are almost identical to the real thing. And yet, the real thing, applied to real fluids, appears to work perfectly. Something is stopping the blow-up. Something in the actual physics of real fluids is preventing the singularities that the math permits. And the question is what that something is, and whether it always holds. In 2004, a paper published in Science Advances found something that I think provides the most unsettling answer to that question. The researchers were studying the mechanism of vortex, stretching, the very term in three-dimensional Navier-Stokes that Ladyzhenskaya could not overcome, the term that allows vorticity to amplify without bound, the source of every mathematical difficulty we have been discussing. What they found was evidence for an intrinsic regularizing mechanism within the fluid dynamics itself. Here is what happens. As vortex stretching amplifies the rotation of a vortex tube, making it spin faster and thinner, the geometry of the flow spontaneously generates a counteracting effect, an anti-twist. The same nonlinear dynamics that create the stretching also create, at a certain point, a restoring force that prevents the stretching from running away to infinity. The fluid protects itself not because the equation demands it. The equation permits blow-up. Tao proved a version of it that does blow up. The mathematics is perfectly compatible with catastrophe, but the actual physical dynamics, the specific geometric interplay of vortex stretching and flow geometry in three-dimensional space appears to generate its own emergency brake. The vortex intensifies, the anti-twist emerges, the intensity plateaus, the singularity is averted, not by a theorem, not by a proof, by the physics itself doing something that the mathematics neither requires nor forbids. I want you to sit with that for a moment, because I think it is the most profound aspect of this entire story, and it is the part that nobody is talking about in the way it deserves to be discussed. We are not just trusting an unproven equation. We are trusting a mechanism inside the physics that we can observe but cannot explain, that we depend on but cannot guarantee. It is as if someone told you that the brakes on your car are not connected to the pedal, but every time you push the pedal, something inside the car spontaneously decides to slow down. It has always decided to slow down. Nobody knows why. Nobody can prove it always will, but it has never failed. So you keep driving. That is the relationship between human civilization and the Navier-Stokes equations. We push the pedal. The physics breaks for us, and we have collectively decided not to worry about the fact that we do not understand why. There is a deeper layer here, and it connects back to something I mentioned at the very beginning that I want to return to now. The Turing completeness of Navier-Stokes solutions. The fact that certain fluid flows can perform arbitrary computations. This means the equation is not merely describing the motion of water and air. It is, in some configurations, processing information, computing, executing algorithms. And some of those computations, by the halting problem and Turing's foundational results in mathematical logic, are undecidable. No finite proof can characterize all of them. What this suggests, and I want to be careful here, because this is an implication, not a proven statement, is that the Navier-Stokes equations might belong to a class of mathematical objects that are too rich to be fully tamed by proof, not because they are badly formulated, not because there is an error in the equation, but because the equation is expressive enough to encode behaviors that sit beyond the horizon of provability. The equation can compute anything. And mathematics has known since Gödel and Turing that systems expressive enough to compute anything necessarily contain truths that cannot be proven within any finite formal system. This is not an indictment of mathematics. It is not an indictment of the equation. It is a statement about the relationship between mathematical systems and the truths they can access. And what it means for the Navier-Stokes problem is that the Millennium Prize question, does blow up occur or not, might have a definite answer that is nonetheless beyond the reach of proof as we understand it. The equation might blow up for some initial conditions and not for others, and no single proof might be able to fully characterize the boundary between the two. I want to acknowledge something here. I am not a mathematician. I am someone who has spent weeks reading papers and blog posts and lecture notes about this subject, and there are people who would push back on some of what I have just said, who would argue that the specific Millennium Prize formulation is precise enough that undecidability is unlikely to apply to it directly. And they may be right. The halting problem does not mean every question about every Turing complete system is undecidable. It means some questions are. And the existence and smoothness question for Navier-Stokes is a specific, well-posed question that might well have a clean answer. But the fact that we do not know whether the question has a clean answer, after 26 years and $1 million bounty, and the efforts of Fields medalists and Abel Prize winners and the greatest mathematical prodigy of our generation, is itself remarkable. And the fact that the equation is computationally capable enough to encode undecidable problems means that the landscape around it is more treacherous than anyone appreciated when the Millennium Prize was announced. The optimism of 2000, when the Clay Institute gathered the world's best mathematicians in Paris and presented these 7 problems as grand challenges for the new century, has given way to something more guarded, something more unsettled. The sense that Navier-Stokes might not yield to a single brilliant insight the way the Poincaré conjecture did. The sense that it might require, as Pfefferman warned, deep new ideas that nobody has yet conceived. Or the sense, which Tao's work has made respectable, to discuss openly that the answer might be the uncomfortable one, that the equations blow up, that they are not, in the mathematical sense, entirely well behaved, and that the only reason civilization has not noticed is that nature has its own way of preventing catastrophe. I have been thinking about the people in this story. Navier, who gave us the equation and lost his bridge and his career. Leray, who could not prove the equation works and then spent 5 years in a Nazi prison camp pretending he studied shapes, while the Gestapo murdered his collaborator. Ladyzhenskaya, who watched the NKVD destroy her family, was denied education and then proved the equation works in a world 1 dimension simpler than ours, only to be stopped cold by the 3rd dimension. Caffarelli, Kohn, and Nirenberg, who proved singularities are almost invisible if they exist, but could not prove they do not exist. Tao, who built a computer out of water and watched it blow up, and who now believes, quietly but publicly, that the real equations can blow up too. Every one of them pushed further than the person before them, and every one of them was stopped by the same thing, the nonlinear term, the vortex, stretching, the fluid carrying its own velocity, amplifying its own motion, computing its own fate. The equation resists understanding in the same way that turbulence resists prediction, not because it is random, because it is too complex, too rich, too capable, and yet we depend on it completely, absolutely, without alternative, without backup, without proof. I keep coming back to Navier's bridge, an engineer who believed mathematics could master the physical world, whose bridge fell into the Seine, and whose government told him he relied too much on math. 200 years later, the entire planet relies on his equation. and the mathematicians tasked with proving it is reliable keep watching their proofs collapse, one after another, like bridges falling into rivers. There is something about the Navier-Stokes equations that feels almost personal the longer you study them. I know how that sounds. They are equations, symbols on a page. But the way they resist understanding, the way they yield partial answers and then snatch the full answer away, the way they work perfectly in practice while refusing to justify themselves in theory, starts to feel less like a mathematical puzzle and more like an encounter with something that has a will of its own. The nonlinear term is the heart of it, the fluid carrying its own velocity. In almost every other equation in physics, the system being described is passive. It sits there and the equation tells you what it does. In Navier-Stokes, the fluid acts on itself. It shapes its own future. The velocity determines the flow, and the flow determines the velocity. It is a self-referential loop, and self-referential systems, as Gödel and Turing taught us almost a century ago, have a tendency to produce undecidable statements and incompletable proofs. The Navier-Stokes equations are not just describing a fluid, they are a fluid that describes itself, and that self-reference might be why they resist being fully understood. I realize I am editorializing. A mathematician would tell me that the anthropomorphization of an equation is not helpful, and they would be right, technically. But there is a reason that Tao described the blow-up mechanism as a Maxwell's demon, language that implies agency. There is a reason physicists talk about turbulence, as if it is an adversary rather than a phenomenon. The equation earns the anthropomorphism by behaving at every turn as if it is actively resisting the attempts of the people who study it. It gives you the two-dimensional solution and then hides the three-dimensional one. It lets you prove singularities are almost nothing and then refuses to let you prove they are nothing at all. It allows you to build weak solutions and then, 85 years later, reveals that those solutions are not unique, that your entire approach was built on sand. If you told me the equation was sentient, I would not believe you, but I would understand why someone might say it. I keep coming back to Navier's bridge, an engineer who believed mathematics could master the physical world, whose bridge fell into the Seine, and whose government told him he relied too much on math. 200 years later, the entire planet relies on his equation, and the mathematicians tasked with proving it is reliable. Keep watching their proofs collapse, one after another, like bridges falling into rivers. There is a pattern here, and I do not think it is an accident. The equation that describes every fluid on Earth, the equation that moves the atmosphere and fills the oceans and pushes blood through your veins right now as you read this, is an equation that contains within it the capacity for infinite catastrophe, blow-up, mathematical singularity, the numbers going to infinity. The math says it can happen. The physics says it does not. And the gap between those two statements is where we all live, where every aircraft flies, where every forecast is issued, where every surgeon makes the cut. Nobody bridged that gap. Navier did not bridge it. Stokes did not bridge it. Leray did not bridge it. Caffarelli, Kohn, and Nirenberg did not bridge it. Tao has not bridged it. 26 years of $1 million bounty has not bridged it. And the July 2025 Turing completeness result suggests the gap might be deeper than a bridge can span. It might go all the way down. The calculations have been checked. The equation is what it is. The nonlinear term does what it does. Somewhere in the mathematics of the Navier-Stokes equations, there might be configurations of fluid that spin themselves to infinity in finite time. Tao thinks so. Ho thinks he can prove it. And if they are right, then every application of these equations, every simulation, every forecast, every aircraft design operates on the assumption that nature happens to avoid those configurations, that the anti-twist always saves us, that the physics always breaks in time. And the reason you were never told this, the reason this is not front-page news, the reason $1 million bounty for one of the most consequential mathematical questions in history generates less public attention than a single cryptocurrency fluctuation, is that the answer does not matter to the people who use the equation. Engineers do not need a proof. They need results, and the results are good. The planes fly, the forecasts work. The blood flow simulations predict outcomes with 86% accuracy. Good enough. Good enough is what we built the world on. But good enough is not the same as proven, and proven is not the same as true. And the space between those words is where the Navier-Stokes equations have lived for 204 years, carrying civilization on their back, holding up everything while $1 million gathers dust in a foundation's accounts, waiting for someone to explain why they work, or to prove that they do not. The equation waits. It has been waiting since Navier presented it to the Académie in 1822, since Stokes rederived it in 1845, since Leray invented weak solutions in a world that was about to go to war, since Ladyzhenskaya proved the two-dimensional case from a country that had tried to erase her family, since Caffarelli, Kohn, and Nuremberg walked through Chinatown and proved singularities are almost nothing, but could not prove they are nothing at all. Since Tao uploaded his paper on a February morning in 2014, and the field realized the standard tools were not enough. The equation waits, and while it waits, it runs everything. The water in your pipes, the air over the wing, the blood in your brain, the weather that will arrive tomorrow, the current that carries the ocean, all of it described by mathematics that permits its own destruction, all of it held together by a physical mechanism that nobody can name, nobody can prove, and nobody, if they are being honest, fully understands. And somewhere in the space of all possible fluid configurations, there might be one that the anti-twist cannot save. One where the vortex stretching outruns the correction. One where the numbers go to infinity, and the mathematics breaks, and the equation that holds everything together stops holding. We cannot prove the configuration does not exist. The greatest mathematician alive believes it does. And if it does, the only thing standing between civilization and a fundamental reckoning with the limits of mathematical knowledge is the fact that nature, so far, has chosen not to put us there. So far,